Hello friend, welcome back to Gradeup. My name is Vikas. In my previous video lecture on power plant engineering, I have completed the entire complete syllabus of power plant engineering, completing with turbine and types of turbine. Okay.
Check out the link below for free GATE course that has more than 200 videos along with this video, followed by doubt sessions, previous paper and more than 250 quiz from Gradeup.
So in this video lecture, I'll be solving some previous year GATE questions on complete power plant engineering syllabus. Okay, in which there will be questions from Rankine cycle, Brayton cycle. Along with that, there will be questions from compressor and turbines. Okay, so let's start with solving some good quality previous year GATE questions. These questions I have taken fresh question from between 2015 to 2018. Okay, so first question from GATE 2015 set 2. In this question, it is given that in a Rankine cycle, okay, the enthalpy at the turbine entry and the outlet are given to you, which is 3159 and 2187 kilojoule per kg. Also, the specific pump work is given as 2 kilojoule per kg. Now, what you have to find is the specific steam consumption in kilogram per kilowatt hour of the cycle based on the net work output. So, you have to find the specific fuel consumption, steam consumption. Now, specific steam consumption is equal to, as you know, that it is equal to 3600 over work net, and the unit is kilogram per kilowatt hour. Okay, so you should remember this formula. The formula is very important, that specific steam consumption is equal to 3600 over work net, and the unit of this net work should be in kilojoule per kg. So as given the question, this work is given to you, work done by turbine. So net work is equal to work done by turbine minus work done by pump. So turbine work is equal to, what is it? It is equal to enthalpy at the inlet of the turbine minus enthalpy at the outlet of turbine. So it will be equal to 3159 minus 2187. And the pump work is given to you. This is equal to 2 kilojoule per kg. Kg. So this will come out to be 3159 minus 2187 minus 2. So this will come out to be 972 minus 2. This is equal to 970 kilojoule per kg. Okay. Now specific steam consumption is equal to 3600 over work net. So this net work is equal to 970. So after solving it, this specific steam consumption will come out to be 3.71 kilogram per kilowatt hour. Okay. So this is a very important formula, that if this formula is very important, that specific steam consumption in kilogram per kilowatt hour is equal to 3600 over net work. And remember that this net work unit should be in kilojoule per kg. Okay.
Subscribe to our channel and press the bell icon to never miss any update from Gradeup.
So this comes out to be 3.71 kilogram per kilowatt hour. Now next question is from GATE 2016 set 1. In this question, it is given that there is a steam power plant which is working on ideal Rankine cycle, and in this cycle the superheated steam enters the turbine at 3 megapascal and 350 degrees Celsius. The condenser pressure is given to you 75 kilopascal. The thermal efficiency of the cycle is, you have to find the thermal efficiency of this Rankine cycle. Also it is given to you that saturated liquid for condenser pressure of 75 kilopascal, value of enthalpy of saturated liquid is given to you, specific volume is given to you, and specific entropy is given to you at 75 kilopascal. Also, the enthalpy change at 75 kilopascal is given to you, and entropy change given to you. Along with that, it is given that at 3 megapascal, okay, which is the turbine pressure, the enthalpy at 350 degrees Celsius, that is a superheated steam, the enthalpy and entropy is given to you. So how we are going to solve this question? To solve this question, firstly you have to draw the diagram. Okay. So on a TS diagram, we will firstly draw this. So this, since it is shown in the question that steam in the superheated state, so it will be somewhere here. Okay, steam is totally superheated. So this is 1, this is 2, this is 3, this is 4. Okay, so we have to find the efficiency, and we know that the efficiency is equal to work done over heat supplied. So work done in this case is equal to H1 minus H2, which is the turbine work, minus H4 minus H3, which is the pump work, over heat supplied. Now heat supplied, this is the heat supplied, so this is equal to H1 minus H4. So how we are going to find this enthalpies? Okay, now enthalpy at point 1, this is the point at 3 megapascal pressure and 350 degrees Celsius. So enthalpy is given to you 3115.3. So this enthalpy is given to you, H1 is equal to 3115.3 kilojoule per kg. Okay, this enthalpy is given to you. Along with that, it is given that the entropy is also given at this point, which is equal to 6.7428. 6.7428. Okay, and entropy is given to you. So we have to find the S2. Now this value of S2 can be found by, as we know that this is an isentropic expansion in the turbine, so S1 will be equal to S2. Okay, so S1 is equal to 6.7428. Okay, now S2 will be equal to SF2 plus X times of SFG2, where SFG2 is the entropy change of vapor minus liquid. So this will come out to be SF2 is equal to, this is 75 kilopascal pressure of the condenser, and this is 3 megapascal. Okay, so SF2 is given to you, this is equal to, this is 1.213, and SFG2 is given to you 6.2434, 1.213 and 6.2434. So this is 1.213 plus X times 6.2434. So after solving it, you will get the value of X dynamic friction is equal to 0.88. Okay, now you can find the value of H2 will be equal to HF2 plus X times of HFG2. So you are given these values are given to you. HFG is equal to 2278.6 and HF is equal to 384.39. So after putting these values, you will get, after putting this value, you will get the value of H2 is equal to, this H2 will come out to be 2389.558 kilojoule per kg. Okay, now we know that the value of H1 is given to you, H2 you have find. Now what you have to find is the value of H4 and H3. As we know that the value of H3 is the enthalpy of the saturated liquid, and this enthalpy of saturated liquid is given to you, which is 384.39. So H3 is equal to 384.39. Okay, now you have to find the value of H4. Now how we can find the value of H4? We know that the pump work is equal to H4 minus H3. Now this pump work is also equal to, we know, the specific volume into the pressure of the boiler minus condenser pressure. This I have told you when I in a video lecture on steam turbine, that the pump work is also equal to specific volume into boiler pressure minus condenser pressure. So specific volume at 75 kilopascal is given to 0.001037. So this is equal to 0.001037 into boiler pressure is 3 megapascal. Okay, so this will be equal to 3000 kilopascal minus condenser pressure 75. So you can get this value, with this value will equal to 3.033225 H4 minus H3. So as we know, the value H3 is equal to 384.39. So from here you can find the value H4. This H4 will come equal to 387.423 kilojoule per kg. Now since you got the value of H4, H3, H1, H2 and H1, you got all this value, you can put this value in this equation, and after putting this value in this equation, you will get the value of efficiency equal to 26, okay, 26.4%. Okay, so this will be the efficiency in case of 26.4% will be the efficiency. Okay, so this is a good question. It based on concept as well as you should remember this formula. Okay, Next question is again from GATE 2016 set 2. In this question it is given that there is a simple gas turbine Brayton cycle and a gas turbine with cycle with regeneration. Okay, in both the cycle the pressure ratio is given to you which is equal to 6 and the ratio of specific heat of the working medium is 1.4. The ratio of minimum to maximum temperature is also given to you which is 0.3. Okay, in the regenerative cycle the ratio of thermal efficiency of the simple cycle to the regenerative cycle is. So you have to find the ratio of the simple Brayton efficiency as well as the efficiency due to regeneration. So you know that the efficiency due to simple Brayton cycle is equal to, as if you remember the formula, it is equal to 1 minus Rp over gamma minus 1 over gamma. Okay, so this, since the pressure ratio is given to you 6, so you can put the value of pressure ratio 6 and gamma is 1.4. So after putting this value, this will come out to be 0.4. Okay, efficiency will 0.4 for a simple Brayton cycle. Now what about a regenerative cycle? I have told you the efficiency formula for efficiency for a regenerative cycle. This is equal to regeneration is equal to 1 minus T minimum temperature over T maximum temperature into Rp over gamma minus 1 over gamma. So you should remember this formula for efficiency of a Brayton cycle with regeneration. Okay, this is a very important formula. Now, since you know the value of ratio of minimum to maximum temperature is given to you which is 0.3. So this is 1 minus 0.3 into Rp which is 6 for same both the things. So this will come out to be 0.499. Okay, so as we know the value of Brayton cycle and Brayton cycle with regeneration, so we have to find the ratio of simple cycle to regenerative which is equal to 0.40 over 0.499 and this will come out to be 0.80. Okay, so out of these options, option B is the correct answer. Okay, so you should remember this formula for regeneration of Brayton cycle. Next question is again from GATE 2016 set 3. Okay, so in this question it is given that there is a 3-stage air compressor. Okay, so the question of a multi-stage compression topic question is that. Okay, so this is a question of multi-stage compression is done in a reciprocating compressor. So I hope you remember that for a reciprocating compressor we do multi-staging. The inlet pressure is P1 and the discharge pressure is P4. Okay, and the intermediate pressure is P2 and P3 where P2 is less than P3. Okay, so there are 3 pressure P1, P2, P3 and P4. Okay, where P4 is greater than P3, P3 is greater than P2, P2 is greater than P1. Okay, so there are 3 stages of compression. Okay, so for this 3 stage of compression, compression ratio will be equal to P2 by P1, P3 by P2 and P4 by P3. Okay, this is the compression ratio if there is 3 stages of compression. Okay, because compression ratio is the pressure ratio of the pressure after compression. So if this is the pressure ratio for the first stage compression, the pressure ratio for second stage, this is pressure ratio for third stage. Now it is given in the question that total pressure ratio of the compressor is P10. The total pressure ratio will be equal to P4 over P1. This is given to you 10. Okay, and the pressure ratio of the stages are equal. For the remaining stages, the pressure ratio is same. That is, this pressure ratio is same. This is the first equation. This is second equation. Now, it is given that P1 is equal to 100 kilopascal, and you have to find the value of P3 in kilopascal. So how we can find it? We know that this is simple mathematics. This is P4 over P1. So P1 is given to you, so P4 will be equal to 10 into 100. So this will be 1000 kilopascal. Okay, so now we know the value of P4. Now you have to find the value of P3. How we are gonna find the value of P3? We know this P2 by P1 is equal to P3 by P2 is equal to P4 by P3. So we will be using this relation. Okay, how we are gonna use this relation? P4 by P1 it is given to you. If you multiply with P2 by P2 and P3 by P3, okay, now if you rearrange it, this will come out to be P2 by P1 into P3 by P2 into P4 by P3. okay, equal to 10. This is simple rearranging, okay. Now, since we know that P2 by P1 is equal to P3 by P2 is equal to P4 by P3, so if this is all equal, so we can write it, since we need to find P3 here, okay, and P4 we already know, so we will be converting this all into P4 by P3, since this ratio is equal to P4 by P3, so this will be equal to P4 by P3 whole cube equal to 10, okay. So after, since we know the value of P4 is equal to 1000, so 1000 whole cube over 10 is equal to P3 whole cube. So after solving it, we get P3 is equal to, value of P3 will be equal to 464.15 kilopascal, okay. So this will be equal to 464.15 kilopascal, okay. So this was a good question, okay, where you require the concept on multi-staging. Now next question is from GATE 2017 set 1. In this question it is given that the pressure ratio across a gas turbine for air having specific heat of 1040 and ratio of specific heat as 1.4 is 10. That is, pressure ratio is given to you 10, okay. If the inlet temperature to the turbine is 1200 Kelvin and the isentropic efficiency is 0.9, then you have to find the gas temperature at the turbine exit. So first thing, it is a Brayton cycle, and second thing, because it is a gas turbine, it is a Brayton cycle. Second thing is that there is an isentropic efficiency in the turbine. That means there is a difference in the actual turbine, there is a actual work and the turbine work. So if you draw this gas turbine on a TS diagram, sorry, this will be somewhat like this, okay. So for a ideal cycle, this is the isentropic 1, 2, 3, 4, okay. This is the isentropic, but actual work will be 3 to 4 days, okay. Now in this question you have to find the gas turbine at temperature exit. Now since isentropic efficiency is given to you in this question, so you don't have to find this T4, you have to find T4 dash. Why? Because there is a isentropic work here, or there is a actual work. So if isentropic efficiency is given to you, then you have to find this T4 dash, which is the temperature due to actual work, okay. Now firstly you should understand that what is given to you. In the question it is given to you T3 is equal to 1200, RP is equal to 10 and isentropic efficiency is equal to 0.9. Now we know that T3 over T4 is equal to P3 over P4 gamma minus 1 over gamma. This is the pressure ratio. This is equal to 10. So this will be equal to 0.4 over 1.4 T3 by T4. So this will come out to be 1.9306 and this T3 is already given to you 1200 Kelvin. So from here you can find the value of T4. This value of T4 will come out to be 621.53 Kelvin. Now since you know the value of T4, but as I have told you, here it is isentropic efficiency is given to you, so you will be using this formula. Isentropic efficiency for a turbine is equal to actual work over isentropic. I hope you remember it, okay. So actual work will be equal to T3 minus T4 dash over isentropic will be equal to T3 minus T4, and this is equal to 0.9. So since you know the value of T3 is 1200, T4 is 621.53, okay, and this is again 1200, so you can find the value of T4. After solving it, you will get the value of T4 dash is equal to 679.38. So out of this given option, this option is 679.28, so this is close to our answer. So this is B, option B is the right answer, okay. So here you have used the concept of isentropic efficiency. So every concept is very important in the GATE exam. Concept is important. It's not that sometimes you will get direct formula, sometimes it is concept based, okay. So you should understand the concept. Next question is from GATE 2017 set 2. In this question it is given that in a Rankine cycle for a steam power plant, the turbine entry and exit enthalpy are 2803 and 1800. Okay, the enthalpy of water at the pump entry and exit are 121 and 124. You have to find the specific steam consumption. So if you will see in this video lecture only, the same type of question was asked in GATE 2015 set 2, and the same concept is asked in GATE 2017 set 2. That means concepts are repetitive, questions are not. Okay, this direct question will not be asked, same question will not be asked, but the concept is repetitive. Okay, so specific steam consumption, as you know, it is equal to 3600 over work net. Now net work is equal to work done by turbine minus work done by pump. Turbine work is equal to enthalpy difference of the turbine, which is equal to 2803 minus 1800. This will come out to be 1003 kilojoule per kg. And pump work will be equal to, this is H4, this is H3, will be equal to H4 minus H3, which is equal to 124 minus 121. This will come out to be 3 kilojoule per kg. So net work will be equal to 1003 minus 3, which is 1000 kilojoule per kg. Okay, the unit you never forget, this is kilojoule per kg. Okay, so if this unit are same, that means you just have to put the value of net work here. So it will be 3600 over 1000. This will come out to be 3.6 kilogram per kilowatt hour. So this option is the correct answer. Option B, 3.6 is the answer. Okay. This question was asked in GATE 2017 set 2. This question is from GATE 2018 set 2. This is a current question which was asked in GATE set 2 of the GATE exam, GATE 2018. In this question it is given that select the correct statement for 50% reaction stage in a steam turbine. So this question is for a 50% reaction stage, and which is nothing but Parson turbine. As I have told you that 50% reaction turbine is called Parson turbine. Now the question is, the rotor blade is symmetric or the stator blade is symmetric. Okay, you have to find the correct option. Is the rotor blade symmetric? Is the stator blade symmetric? If the absolute inlet flow angle is equal to absolute exit flow angle, or the absolute exit flow angle is equal to inlet angle of the rotor blade. Okay, so which answer is correct to you? So as I have told you in the last video lecture of my power plant engineering, in which I have taught you about different kinds of turbine. In that I have told you that for velocity triangle of a Parson turbine, the inlet nozzle angle is equal to outlet blade angle, and the outlet nozzle angle is equal to inlet blade angle for a Parson turbine. So this is important. Now see from this option. Also I have told you that the blades in case of a reaction turbine are not symmetrical. Okay, since blades are not symmetrical, these two options are not correct. Okay, now next are two options: absolute inlet flow angle. Inlet flow angle is equal to absolute exit flow angle. Okay, now this option is not correct because here both absolute inlet flow angle and absolute exit flow angle are given to you. That means alpha 1 is equal to alpha 2. This is not correct. Okay, for a reaction turbine. Next part, D part, it is given that absolute exit flow angle, that is alpha 2, is equal to inlet angle of the rotor blade, which is beta 1. Okay, since it is given this is a Parson turbine, 50% reaction stage turbine, and for a Parson turbine this alpha 2 is equal to beta 1, that means this option is correct. Okay, so every question is important, every concept is important. And this concept I have told you in the last video lecture of turbine, in which I have taught you velocity triangle. Okay, so this is very important concept. So as you can see from the, if you analyze from the previous year GATE questions, concept is important. Direct formula can also be asked for a power plant engineering. Okay, so with this I complete the entire syllabus of applied thermodynamics, and we have solved some good quality questions for power plant engineering. Okay, so if you have any query, if you have any doubt regarding this subject of power plant engineering, you can post your query or comment on the Gradeup app. Okay, you can also practice free quizzes on all the topics of thermal engineering, okay, or all the topics of mechanical engineering on the Gradeup app. Okay, you can also join the test series, which is a very good test series based on latest questions and good quality questions on the good concept, okay, that may be asked in the GATE 2019 exam. So you can also join Gradeup test series. So this is all for today. Thanks for listening. Have a nice day. Thank you.